This is Algebra 2, Lesson 5.3. We are solving quadratic equations by finding square roots. Those are our goals. We're solving quadratic equations, and then we're solving real-life problems like falling object problems at the end. 264 is where it begins. First thing we have is a handful of definitions. First one is a square root. A square root, or a number r, is a square root of a number s if r squared is equal to s. So what this is setting up for us is it's setting up the fact that square roots are undone by squaring something and vice versa. Squaring something is undone by taking a square root. That's how you undo each of these. Those are the inverse operations. So if r squared is equal to s, then r is a square root of the number s. The radical sign is that actual check mark looking thing right there. Okay. We will get into other roots besides square root into this course, or later on in this course, where it'll say cube root, or the fourth root, or the fifth root, but that's coming later on down the line. For right now, if there's no number right there, if it just says right that, it's assumed to be the square root. Just like if something is raised x squared, it means x squared. But if you don't see any value right there, you know that that's x to the first power. So for right now, like I said, if these are all going to be square roots, there's nothing shown. It simply means the square root of something. The radicand is whatever is under the radical. This is the radical itself, but this number here is the radicand for. So if you see that term radicand, that's what it means. The radical is the entire thing. So right here, the sign is the symbol itself. The radicand is what's underneath it. The radical is the entire thing. So the square root of s, the entire thing, that entire part of the expression is the radical. And if something has a radical in it, it is considered a radical expression. The square root of 2 plus 3 equals whatever. This is a radical expression because it has a radical in it. Just like x plus 3 equals something, this is a variable expression because it has a variable in it. Rationalizing the denominator is something that students struggle with, even though it is very, very simple. You cannot have a radical at the bottom of a fraction. It cannot be in the denominator. And since it cannot be in the denominator, the only way to undo that is to multiply it, if it's at the square root of 2, to multiply it by whatever that is, the square root of 2 over the square root of 2. In actuality, this is multiplying by the number 1 because something divided by itself is 1. So that doesn't change your problem. It just changes the form of the number, which makes it acceptable. So rationalizing the denominator. Anytime there is a radical that you cannot simplify at the bottom, anytime there's one that you cannot undo and get rid of completely, you need to rationalize it by multiplying by whatever it is over itself. Here are our properties of square roots. Now this is talking about a and b both being greater than 0. So a and b both being not 0 and being positive. So the square root of a times b is equal to the square root of a times the square root of b. What this means is the square root of 27. That can be separated into the square root of 9 times the square root of 3, which gives us 3 times the square root of 3. That's the reason you do that. That's the product property. It means you can separate a big number into the multiplication of two smaller numbers. The quotient property does the same thing. It's about separating the square root of a over b. Notice it's a fraction under a radical. That's not allowed. You cannot leave a fraction under a radical like that. That is the same thing as separating it into the square root of a over the square root of b. So the product property separates it using multiplication. The quotient property separates it using division. Let's look at an example like that. It says simplify the expression. The square root of 27, that's a coincidence that I said that a minute ago, is equal to the square root of 9 times the square root of 3. Now somebody might be asking or thinking to themselves, why the square root of 9? Why did we use that number to separate it? This is the reason. Perfect squares Oh, when you count by numbers and you multiply those numbers times themselves. This is what I mean. 1 times 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5, 6 times 6, 7 times 7. Those numbers make your perfect squares. 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. 6 times 6 is 36. 7 times 7 is 49. Those numbers continue on and on and on. Those are what is considered, or those are what is considered perfect squares. A perfect square that is a factor of 27 is the number 9. So you multiply 9 times 3, or more specifically, the square root of 9 times the square root of 3. Because all this symbol means, when you're talking about square roots, is what number times itself. It just means what number times itself. And the square root of 9 means what number times itself. We all know the number is 3. So 3 times the square root of 3. B says the square root of 5 times the square root of 15. So when you multiply the two together, you get the square root of 75. Now you're back in a similar position we were at the beginning of A. The square root of 5 has a perfect square factor, 25. Remember, go back to these numbers. These are the numbers you're checking to see if one of them is a factor in 75. You want the largest one. But remember, if you don't pick the largest one, it's just like simplifying a fraction. You can do it again. A factor of 75 is 25. So the square root of 25 times the square root of 3, which gives you what number times itself? 5 times the square root of 3. C is a fraction. The square root of 5 over 36 can be separated. This is the quotient property into the square root of 5 over the square root of 36. And again, the square root of 36 means what number times itself, and that's why 6 is there. Notice it's not the square root of 6 on the bottom. Notice that. It's just 6. This is considered simplified, the square root of 5 over 6, because the three questions you need to ask yourself to see if it's simplified, you get no for all of them. The first question, is there a perfect factor inside of 5? Remember, your perfect factors are the ones we listed at the top. None of those numbers multiply by anything to give you 5 other than 1, and 1 doesn't change it anyways. So you go past 1 and use 4, 9, 16, 25, you use those numbers. None of those numbers goes into 5. The next part is there's no fraction under the radical. There was when we started, but we changed it. We don't have it anymore, so we got no. And the last part, there's no radical in the denominator, which there is not. That's why the square root of 5 over 6 is simplified. The last one on this one says, let's take it a step at a time. The square root of 13 over 3. The first thing you do is separate it into the square root of 13 over the square root of 3. That's the quotient property. Now, unlike the last problem where we had a perfect square at the bottom, 36, and we could take out the number 6, we don't have that here. So we have to do what's called rationalizing the denominator. Whatever's at the bottom, in this case it's the square root of 3, you multiply it by that over itself. So the square root of 3 over the square root of 3, that's what we're multiplying it by. If you go straight across from here, the square root of 13 times the square root of 3 is the square root of 39. And when you put these two together, now this is kind of a shortcut. Anytime you have the same exact radical multiplied by itself right here, they're both 3, you can pull it out and call it 3. Just take it right from under the radical. If that doesn't make sense to you, multiply them by each other. The square root of 3 times the square root of 3 gives you the square root of 9, and the square root of 9 is 3. Okay, but it just helps you the way you have less arithmetic to do. You have bigger, smaller numbers. You don't have to deal with quite as big of numbers if you can see the same number times itself or the same radical times itself. So again, the same 3 questions you get. No, there's no perfect factor in 39. There's no fraction under the radical, and there's no radical at the bottom. On the back, everybody, simplify the square root of 500. Remember your perfect factors. 2 times 2, 3 times 3, 4 times 4, 5 times 5. Get used to these numbers, everybody. 6 times 6, 7 times 7, 8 times 8, 9 times 9, 10 times 10. You can at least get used to those numbers. You can go past those, and you will sometimes. But which one of those numbers is a factor of 500? The easiest one to use, clearly, is the number 100. The square root of 100 multiplies by the square root of what? 100 times what? 5. And what is the square root of 100? What number times itself is 100? 10 times the square root of 5. Ask yourself, there are 3 questions. Is there a perfect factor in the square root of 5? No, 4 and 9, and then it's too big. There's no fractions involved at all, so this is considered simplified. 10 times the square root of 5. The number that you got on your calculator when you punched it in is not the correct answer. That is an estimate of the answer. 10 times the square root of 5 is the correct answer. Okay, next to it, do this one. 3 times the square root of 12 times the square root of 6. Okay, for this one, it says 3 times the square root of 12 times the square root of 6. What you want to do is, instead of putting it together, what you could have done, you could multiply those two numbers together and get 72, and then break that down. It might be easier to deal with smaller numbers. Break this one down using the product property into the square root of 4 times the square root of 3. Don't forget to bring this 3 down. That's the only concern people have with that, is they'll forget to bring the coefficient 3 down. So 3 times the square root of 4 becomes 3 times 2 times the square root of 3, which when you put these two together is 6 times the square root of 3. Don't forget to bring this down, times the square root of 6. So now you put them together. The square root of 3 times the square root of 6 is the square root of 18. So don't forget this one, 6 times the square root of 18. And then the perfect square that's in 18 is 9 times 2. So again, don't forget this, 6 times the square root of 9 is times 3 times the square root of 2. And finally, 6 times 3 is 18 times the square root of 2. There's your simplified version. Again, there's a lot to doing this, even though it's simple. But the danger with this is, since there are a lot of pieces and parts, just like anything where there are a lot of parts to it or a lot of steps to it, you could make a mistake. Notice that's why I draw those little lines. Draw those little lines so where you don't forget to bring things down that you're not actively working. Like when we were actively working the square root of 18 and we made it the square root of 9 times the square root of 2, we weren't working with the 6 outside. So bring it down before you forget it. On side of those, do this one. The square root of 25 over 3. The first thing you want to do with this problem is separate it using the quotient property, the square root of 25 over the square root of 3. Remember, you cannot have a radical at the bottom. 3 is not a perfect radical, so you can't pull anything out of it. So the only way to get rid of that radical is to multiply it by whatever it is over itself. So the square root of 3 over the square root of 3. The square root of 25 times the square root of 3. The square root of 25 can be separated into 5 times the square root of 3. All I did was took the square root of 25 over the square root of 3 times the square root of 3. That's the same radical. So remember, the shortcut is to simply write it as 3. Or if you multiplied it across, you would get the square root of 9, which would go back to 3. The last thing you have to check to make sure before, besides the fact that it's simplified, is make sure that there's no number that goes into both 5 and 3. Like if those simplified one more time, just like a regular fraction would, simplify it. They don't in this case. So 5 square root of 3 over 3. One more to do. The square root of 2 over 11. Okay, another simple problem. First thing you want to do is separate it. The square root of 2 over the square root of 11. We just took from the big one and made it two small ones. Neither one of those is perfect squares. We had 25 a second ago. We don't have that here. So remember, whatever's at the bottom, the square root of 11, multiplied by that over itself. The square root of 11 over the square root of 11. Multiplying straight across, the square root of 2 times the square root of 11 is the square root of 22. And the square root of 11, remember, it's the same exact radical. So whatever the radicand is, in this case 11, goes at the bottom. There's no perfect squares in 22.